Okay, so last time we talked about atomic orbitals. Okay, so we were looking at the principal quantum number n and the angular momentum quantum number L. The magnetic portion of that angular momentum quantum number was m sub L, and then the tiny little spin on the electron, plus or minus a half. Yeah. So we had the electron in these orbits. It can be spin up or spin down, and when you get to CHEM, we'll talk about the energy differences that you get from that, called spin-orbit coupling. Okay, so now we're going to build the electron cloud for atoms, and we're going to make what's called electron configurations. So here's the Alex report for the ones that are due tonight. So good job. I see a lot of people have started it already. It always makes me nervous when it's due tonight and I see this yellow bar that's up at like 32 people haven't started yet. So good job. You took my advice and got started on it. Okay, so then these are the topics. We covered these in Monday's lecture, so you guys are ready for today's, and then we're going to finish this out today and start on the one that's due on Monday. So just as a review, I put this in the notes just so it'll be in this note pack. Okay, not going to re-lecture over this, but this is the principal quantum number n, starts at 1 and goes up to infinity. This is the angular momentum quantum number. So this is how the electron cloud looks as you go around in longitude and latitude, kind of like thinking about around the Earth. This is your angle around the Earth. The principal quantum number would be your altitude, up and down. So this is principal quantum number is what shell the electron's in, how far away from the nucleus it is, and the angular momentum is what it does with the angle around the nucleus. And then there's we call those S, P, D, and F. So we start out with S, 0 fingers, S, P, D, F. So that's, you can see that the L quantum number, that's the way I remember it. We don't do much with the M sub L's, but that tells you how many of those orbitals there are. So if you have an F orbital, then you go, F is 3, so you go from plus 3 down to minus 3. So that's going to be 7 M sub L's, okay, because 0's in the middle. And then we have the electron spin plus or minus a half. This gives us these shapes. The angular momentum quantum number, the L's give you these shapes. And these are the M sub L's, minus 3, minus 2, minus 1, 0, 1, 2, and 3. And so that's where we get the different shapes. Each one of these orbitals can contain 2 electrons. And so in the F subshell, we have 14 electrons possible. In the D, we have 10. In the P, we have 6. And in the S, we have 2. And so that's going to be super important today, because we're going to fill all of these different orbitals with electrons and calculate the electron configuration for all the atoms in the periodic table. So this is the capacity. These are some of the problems that we didn't get to on Monday. So let's go through these real quick. What's the capacity of these electron subshells? So here we have a subshell, a 3D. What makes it a subshell? Well, because you have the shell equals N. So this is the third shell, okay? And the D part of that shell is what we call a subshell, the D subshell. Okay, so the principal quantum number is 3. The angular momentum quantum number, it's D. So we started with S, P, D. So L is equal to 2. All right. We'll see you guys on the exam doing that, I'm sure. The maximum number of electrons in this. So L equals 2. So the for this one, M sub L is equal to minus 2, minus 1, 0, 1, and 2. And there's 2 electrons in each. So that's equal to 10. So we have a maximum of 10 electrons in the 3D subshell. Okay, let's go to the next problem. So N equals 5, because it's a 5F. Okay, F orbital. So S, P, D, F. L equals 3. Okay. And so here we have 3. So M sub L goes from -3 to +3. So that's going to be 7. So that's going to be 7 orbitals times 2 electrons. 14. Okay, for the 4p subshell, N equals 4, SP, so L equals 1. We have 3 orbitals times 2 electrons equals 6 total electrons. So we can put 6 electrons in the p shells. You can see this on the periodic table. Over here, the S block is the first 2 columns. All of those are filling up s orbitals. Then we get over to the right, that big square over there. Notice how there's 6 columns over there. Those are the p shells, subshells. And so we're filling up the p orbitals over there, and that's why there's 6 columns over there. And in the middle, we're filling up the d orbitals. So there's 10 columns of the transition metals. And when you get to the F block, there's 14 columns. So every one of those columns has another electron in it, and we're filling up those shells. So you can just, that's how the periodic table was configured by the chemistry, and the chemistry is governed by the valence electrons, and the valence electrons are filling these subshells. So this periodic table reflects what we can put in the orbitals. Okay, so let's sort out the energy of the orbital subshells. So knowing the subshells of an electron shell. So here we have the shell, N equals 2. What are the possible subshells? Remember that L is equal to, starts out at 0 and goes up to N minus 1. And so when N equals 2, L starts at 0 and goes up to N minus 1. So that would be 1. So we have L equals 0 and L equals 1. So that would be an S and a P. So we have a 2S and a 2P. Those are the only subshells that we have. So that's what you would enter in Alex. Now let's look at the periodic table if this makes sense. So we've got row 2, okay, lithium and beryllium. That's the 2s, and we can put 2 electrons in the 2s, and we don't have any d orbitals on that row. We get over there, we have the 2p orbitals from boron to neon. Okay, so in that shell, we can have 2 subshells. We can have an s subshell and a p subshell. Okay, now for the 3, L equals 0, 1, and 2. So we have a 3s, a 3p, and a 3d. But we cannot have a 3f. Why not? Why no 3f? Well, N equals 3, and therefore L equals 0, 1, and 2. This is N minus 1. So L is bound by N. If N equals 3, we can't go above 2 for L. So we have S, P, and D only. We don't have an F. So this F block here, that first available F block has got to be the 4F. It can't be the 3F. Okay. And this first available D block has to be the 3D. It can't be the 2D or the 1D because you can't have a 1 or a 2D. Let's do 4. You know, we can go 4S, 4P, 4D, and 4F. So those are the allowed subshells for N equals 4. So this is pretty simple. Once you figure out that L is bound by N, and once you know N, then you can figure out what L, the range of L values. Okay, the last one for Alex that's due tonight. So a neutral atom has the following electron configuration. So here we're getting into this term electron configuration. So we're about to learn a whole lot about electron configurations. Okay. And so here's some questions we have about it. What's the chemical symbol for the atom? Okay, this says it's a neutral atom. So what do we know about neutral atoms? The number of electrons equals the number of protons. Does everybody agree with that statement if it's neutral? Yes. Okay. So these are the number of electrons right here. So 5, 6, 7, 8, 9. So equals 9 protons. All right, so that's simple. We go to the periodic table and we find 9. So that's element F. So this is fluorine. 9 protons. My eyes are bad. Is that correct? I can't.
Yes.
Okay. I need my glasses for that. Okay, how many electrons does the atom have? Well, we just figured that out. Also 9 electrons. Okay. How many 2s electrons are there in the atom? Well, right here we're showing that this is the 2s orbital and it's filled with 2 electrons. So 2 electrons. Okay. So these are just, again, questions about our little diagram, our little notation. So this is our electron configuration notation. So we write the principal quantum number, the L quantum number represented by letters, and the number of electrons that are in that subshell. So that's what we call a configuration. Now, we're not getting into the, so this is like P5, right? That's the configuration. There's lots of ways to make that configuration. We could have P5, sorry. We could have it like that. We could have it like this. We could have the middle one be the single electron. Okay, these right here statistically are called permutations. So this word configuration is an important word. It's a statistical word. So we don't care when we're building configurations, we don't care what the individual picture is of where that single electron is, okay, by itself. That would be the individual permutation, or what we call a microstate, okay? We're just talking about the configuration that has 5 electrons in the P subshell. That's all I'm doing right there, is just sort of giving you some extra vocabulary. That concept's not going to be tested in this course, but it will be in PChem. But I'm just saying that this word configuration is specific to statistics. Okay, whenever you have a lot, let's say you're flipping coins and you flip 1 head and 3 tails, and the configuration would be 1 head and 3 tails. The permutation would be whether that 1 head came first, second, third, or fourth. Right? There's 4 ways to get 1 head and 3 tails. You can get it first, you can get it second, you can get it third, you can get it at the end. Those would be permutations. But the configuration would be the situation of having flipped a coin 4 times and you got heads once and tails the other 3 times. That's a configuration. So that's what we're working on with the electron configurations. We don't care what the individual way of putting those 5 electrons are in the 3p orbitals. We're just talking about we've got a P subshell with 5 electrons in it. Okay, so now let's start working on the stuff that's due next Monday. Yeah, that's right. So we're going to get into electron configurations. So this is the way we're building up this electron cloud. Makes perfect sense. Okay, you've got a positive nucleus and you got a bag of electrons. And you're going to drop those electrons onto that atom. And what's the first electron going to want to do? Get as close to the nucleus as possible. So it's going to go into the 1s orbital first. And then you take the second one and you drop it in. And it's going to pair up with that other electron and go into the 1s orbital. Now that orbital's full. And so you drop in another electron and it gets as close as it can. It goes into the 2s orbital. You can see the energy here. 1s is lowest, 2s is next. And so we're going to build this up from the lowest energy all the way up. And that building up of the electron cloud is called the Aufbau principle, the building up principle. Roster? Yeah. So, So let's practice. So let's write the electron configuration for these different neutral atoms. And so I'm going to go ahead and draw it on this diagram. So I'm going to put, so first of all, nitrogen is over here. It's got 7 electrons. So we're going to put 7 electrons into this energy level diagram. 1, 2, 3, 4, 5. Watch carefully. 6, 7. So they want the individual seat at the table. they want to spread out. If you look at those p orbitals, they go in x, y, and z. And I don't want, electrons aren't going to want to share the x-axis. Put one in the x-axis, the next one wants to go in the y-axis, and the third one wants to go in the z-axis. So they surround the atom first, and then they have to pair them up. So the 8th electron would have to pair up with somebody. But we get to 7, we've got a really nice situation. And that would be a microstate or a permutation for nitrogen. But the configuration would just be 2p3. So this is going to be 1s2, 2s2, 2p3. And that's the electron configuration. Okay, now let's do sodium. We can leave everything that we have on that chart. We just go past nitrogen and get to sodium. Now sodium has 11 electrons. So we've got 7 in here. So we'll start counting from here. 7. This is 8. This is 9. This is 10. And then sodium has that 1 and the 3s, 11. Okay, so this would be 1s2, 2s2, 2p6. We filled that one up, and then we have the 3s1. So it's got that 1 extra valence electron in that 3s orbital that's way far from the nucleus. So we looked at the size of the sodium atom relative to the ball at target, and this again would go from like New Mexico to across Louisiana. I mean, it's huge, 971 miles in diameter if that ball at target was a proton. Now, this is going to get tedious if we have to write this out for all of these, especially mercury. So one way we can simplify this, notice that once we get past 2p6, then all of this is the same every time. See if you can figure this out. What atom has this electron configuration? 1s2, 2s2, 2p6. So this is neon. And so we can simplify this by just taking this out and writing the noble gas in here. So we could write neon in square brackets. So for sodium, we could just write this, neon. So the neon core of the electron cloud. And then we go to the next row, and you see that 3? That tells us what s orbital is next. So we see neon, and then we jump in at the 3s1. So if I have the periodic table, I can quickly write my electron configurations. All I got to do is I got to find sodium. Here's sodium. It's element number 11. So I go over here to the noble gases, and I find the noble gas that's just prior to that. Neon is 10. So I can put the neon core in square brackets and then start here with sodium, and I'm on the 3rd row, so it's a 3s1. Okay, let's do vanadium now. Okay, so here's vanadium. It's element number 23. I work my way backwards in the periodic table, and I get to argon. Okay, so vanadium, we can start with argon. And then I come around here, and I'm on row 4. So it's 4s, 2, and then 3d. How do I know it's 3d? Well, if we look at this, we've filled up all of these. And that right there is argon. And then we have 4s2, and then vanadium is the 3rd one in that block. So 1, 2, 3, 3d3. So that's vanadium. And I really like for you to learn how to use the periodic table to do these, because you'll always have the periodic table. Okay. Now, in terms of knowing that that's the 3D, this little handy tool that we have after the 4s, which we can see on the periodic table for vanadium, I see that's the 4s. But then once I hit the D block, I've got to know what's next. And this little tool shows you that that's the 3D next. Okay. Even though it's on row 4, it's a 3D, and it's dropped down just because of energy levels. So we've moved that down just to show that its energy is just above the 4s. So we go to 4s, and then we get to the 3D. Let's do mercury. This one's really, look how far that is. That's 80 electrons. If we didn't use the noble gas core, that would be a mess. 1s2, 2s2, all the way up for 80 electrons to get to mercury. Okay, but mercury's pretty easy if we use the noble gas core. So it's element number 80. So what's the previous noble gas? Xenon. Okay, good. You see that? And so we have xenon. Okay, then we come around here from xenon, and we're at the 6s. So we have 6s2. If we're past that, it's full. So it's 6s2. Then we have this little star here. And that little star indicates we have this block of F orbitals here. So we get to lanthanum, 57, 58 is cerium. And so then we got to go past all of those. Now, what is that block? What's the first available F block? Well, we've got this little tool here that tells us it's the 4F. Okay, right here. So after the 6s, we have the 4F. And we're past that, so it's full. How many electrons can I put in there? Gee, I can't remember. So I count them. 1, 2, 3, 4. There's 14 of them. Okay, so 4F, 14. And then we get to the Ds. And so we got to figure out which D that is. Remember, the D groups are like drop down a row. So if that's the 6th row, that's the 5 Ds. We also have this little handy tool, the 5D. And then you count up what column you're in. So if that's the D block, you can go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So it's the 5D10. And that's mercury. So even though it's like way down on the periodic table, we can figure out the electron configuration. And it's super big atom. I haven't done mercury like in terms of Huntsville and the target ball, but it's enormous. If sodium is as big as Texas, I can't imagine how big mercury is. So those are electron configurations using this Aufbau building up. Aufbau is German word for build up. Okay, so construction principle, constructing the electron cloud. Okay, so now we can answer some Alex questions. This neutral atom has this electron configuration, Ne3s2. What's the chemical symbol for the atom? These, once you get it with the periodic table, these are super easy. So what is the 3s2? There's row 3. 1, 2. What's the second element? Magnesium, Mg. Okay, how many electrons does that atom have? Well, you could look at it. It's neutral, so that Mg has 12. Now you could add this up. The neon has 10, and then another 2. But still, you could just look. Once you find this chemical symbol for that element, you can go over here and you can look on the periodic table, and you see it's the 12th element. Okay. How many 3s electrons are there in this atom? 2, because it says 3s2. So Alex is giving you little baby steps, right? If these problems seem deceptively easy, they're not trying to trick you, okay? But they're just ensuring that you understand when we write out neon 3s2 that you understand all the different parts, okay? For this last electron in magnesium, what is the L quantum number? The L quantum number. Remember, the L quantum numbers are the letters, S, P, D, F. And so S would be 0, okay? If it was a P, it would be 1, etc. Okay. So let's practice. Let's do the electron configurations for all of these. And we'll do some ions as well. So chlorine. We look at chlorine. We find the previous noble gas, neon. Okay. And then we start on row 3, so that's the 3s 2, and then we're over in the 3p block, 3p, and we're in the 5th column, so 3p5. Now, how many valence electrons does it have? Well, it's this outer shell, so 5 and 2 is 7. Right? And so we see up there the Roman numeral 7, and then in our other periodic tables, it would say 7a. Okay, let's do krypton. Krypton is the noble gas. You could write this, but that's kind of cheating. Okay, but let's not do that. Let's write it all out. So I guess we could do argon. Yeah, we could do the argon core. And then we come into the 4s, 2, and then we have the full, we're past the D block, so that would be 3D, 10. So here we got the 4s, the very next one is the 3D, and we got 3D10, and then we're at 4p6. Okay. Now, people could argue whether it has 18 valence electrons or 8 valence electrons, but anyway, we would typically say 8. But when you get to inorganic and you're starting to talk about the d orbitals, instead of the 8 octet rule or the 8 rule, you have the 18 rule, rule of 18. So everything would like to have 18 electrons if it's in the metals. Okay, arsenic. So here we are, arsenic. It's the argon core. Okay, and then we come in on the 4s row, 4s2. We are past the D elements, and so that's 3D10. And then we have 1, 2, 3 in the P. So back to 4, 4P3. Any questions on that? That should be, are you following along with the periodic table? Yeah. Okay, let's do one that's really hard. Uranium. My goodness. Okay. So uranium is over here on the F group, is 92, L92. So we got to go back over here. So here we come in to 88, 87. And so the previous noble gas is radon, 86. So that would be the radon core. All right, and so after radon, we come in on the 7th row, so it would be 7s2. And so we're going to need to use our handy tool. Here's 7s. The very next one is the 5f. Okay, and so that would be where we are in terms of uranium. We're coming in on the 5f, and it's 1, 2, 3. Okay, 5f3. Where's my pencil? So that would be uranium. Okay. Does that make sense? Now, there's some funny business going on here with lanthanum and actinium, and we'll look at that in a second. Let's start doing ions. So calcium 2+. So there's calcium. It's going to be the argon core, and if calcium has lost those extra 2 electrons, it's the argon core. So calcium 2+ is just argon, the electron configuration for argon. O2-. So where we are up there with oxygen, if I have 2 more electrons, it's the neon core. So you can kind of see why oxygen wants to be 2- and calcium wants to be 2+, because they have the noble gas electron configuration. Let's go ahead and write oxygens out. Let's see, we could do the helium core, 2s2, 2p6. Okay, so this is another way to write the oxygen one where you can see the valence electrons there. It has 8 valence electrons. Let's do iodine, iodide minus. I minus is the same as xenon. Let's do oxygen plus. So here we're going to have to use the helium core. And it's going to come in on the 2nd row. So we have 2s2. Oops. And it's oxygen, which has 8 protons, 8 electrons, but we've lost one of those electrons. So it has really got 7. So it's going to be 2p3. and that's isoelectronic. With what? So that O plus has the same electron configuration as what element? As nitrogen. It's moved left one. We've lost that electron, so now it has the same electron cloud as nitrogen. So with nitrogen. Okay. Good practice, okay? So I like the OpenStax book. One, it's online, it's easily searchable and so on. And it has some really good graphics. Like this is a graphic taken from the OpenStax book. If you wonder where that is, I think there's a link to it in the syllabus, and maybe on the Blackboard page. But it's a free online textbook. And here you've got everything labeled. You know, the S block, because whenever, let's say we're at strontium, it's going to be the 5s2. If we're at francium, it's going to be the 7s1. So this is why I call this the S block. You know, and the S1s all want to lose those electrons and become like the noble gases. So that's why they form +1 cations, those alkali metals. The alkaline earths are S2s. If they lose both of those electrons, they're like the noble gases. And so they want to be +2 cations. You get here in the middle, this is the D block. So you can see the 3D comes in on row 4. Then the 4D is on row 5, the 5D is on row 6, etc. And then here's the P block. When we're over here, we're filling that P subshell. And so if I'm at tellurium here, I know that's going to be the 5p4. That's going to be the last thing that we see is that 5p4. Okay. Now here's a nice tool in your notes that has all of the electron configurations for every element in the periodic table. So you can, at least the last pieces of them. It doesn't have the cores, but you can put the core down and then write this last piece. So if you're practicing, this is a great way to check your work. And so that's in your notes too. So this gets to the uranium one, and we can see that we did a 5f4, but this is slightly different. This little has a 6d1, and so we were off a little bit because this F group kind of comes in after this first column of Ds. So that's a little funky business that's going on with the F block. Okay, we put one electron in the D subshell, and then we start the Fs. It's energetics. It's just the rule is off a little bit. Nature wants to do its own thing, right? We come up with this handy tool, right, where it says after the 6s, I go straight into the 4f, and nature goes, it's not so fast. I kind of want a D electron, but after I get one D electron, then you can start filling the 4fs. It's just why, I don't know, but nature is that way, and it's going to take the lowest energy structure as possible. So it does kind of make sense that an electron could be in the D and have its own independent little view of the nucleus, and then we can start putting them in the F orbitals. But again, we're just kind of waving our hands to come up with a reason to explain what nature's doing. But that's the way the F block is. We can zoom in on some other exceptions too. So there's this F block exception. And you can kind of see that the lanthanum starts out with the 5d1, and then before it gets to 5d2 with hafnium, we have the whole F block stuck in there. Okay, and so we go from lanthanum, then we go to the lanthanides. All of those F blocks are called the lanthanides because they're on the lanthanum row. And then these next ones, the uranium, all of those things are called actinides because this is actinium. We fill that 6d1, and then we take a side trip, fill up the 5fs, and then we come back for Rutherfordium after Rutherford, who discovered the nucleus. Then we have this 5f14 filled, and we start doing the 6d2, 6d3, 6d4. Okay. Alex is probably not going to test you on the F block, okay? But it's still, we're doing electron configuration, so why not show you the whole periodic table? That's what I'm doing. Now, you will be tested on this. There's some exceptions because electrons like to have their own independent view of the nucleus. They want their own orbital, okay? And I have over here these s electrons there's 2 electrons in the s orbital, and we get close to filling all of or half of the d orbitals, and when we get to chromium, notice this vanadium is 3d3, chromium and molybdenum and tungsten and seaborgium should be a D4. Okay, but look at that. Chromium's a D5 and molybdenum's a D5. Where did it get that extra electron? It stole it from the S subshell. So look at chromium. It's an exception to our filling rules. Vanadium was 4s2, 3d3. Chromium is 4s1, 3d5. So we got close enough to a half-filled subshell, and we grabbed an electron out of the S to make sure we had a D5. That's very stable. Every electron there has its own orbital that it can interact with the nucleus with. So the chromium group is an exception, at least chromium and molybdenum. It looks down here like the D4s. You know, these guys are not an exception. So we have the S2 and the S2 on these big ones. So I really should just draw the box right there. So these top two rows, they steal an electron from the S orbital and move it over to the D orbital, so we could have a D5, half filled.
Is that the same thing with NB?
Where?
Because NB is a 14-4 versus
No, it follows the rule. Yeah. And so then we do the same thing over here for copper. Okay, copper, silver, and gold. They steal an electron from the S subshell so they can be fully filled on the Ds. So copper gets close to enough to a D10, and it says, I'll go ahead and fill up my D subshell by taking an S electron. So that's what nature's doing. There's really, we just say that fully filled and half-filled subshells are stable. They let the atom drop in energy enough that this is what happens. So again, we really love those sp and d orbitals in general chemistry, not so much on the f orbitals. So here we have, we start by putting an electron in that d orbital, but when we get to cerium, we take it back. So cerium's an F2, praseodymium's an F3, etc. Uranium still has that S61 and a 5F3. So again, the F block is kind of a mess. Okay, so I'm not going to test you on the F block, but I will test you on those two exceptions, the chromium group and the copper group. Steal an S electron. Yes?
Could you say again why NB 41 is not?
Right here. It's following the...
jumps from 4 to 2 to 4.
Oh, yeah, that is a weird one. Yeah. So I'm going to put a question mark on that.
Because then it makes like RU47.
Yeah. So this one.
If you're counting, it gets off.
Yeah. It actually. I mean, it adds up to 41. Like, see, this is S2 D2. This should be S2 D3, but it's S1 D4. I don't know. You guys have got good eyes. I didn't notice that. Yeah. So that's a weird one. So this is telling you this is telling you what nature's doing, and the rule applies. I mean, there's roughly 100 elements. The rule applies to 90 of them, 95 of them. So that's pretty good rule. So this little handy tool that we're talking about will work on 95% of the periodic table. But you've got some exceptions. Now, I would like for you to learn the exceptions for chromium and molybdenum, and for copper and silver and gold. Okay, so tungsten's not an exception, and don't worry about niobium because I don't even know about that one. That doesn't make any sense to me, really. But anyway, and I just show you this strange thing of the F group being inserted after the D ones. It's a little strange too. Okay, and then here we get to, we're instead of pulling we've got this half-filled F shell, and here for gadolinium and californium, we instead of going to F8, we put that electron back in the D1. So it's very strange. So let's look at these exceptions. And so this is what's happening. Tom and Jerry, Tom says, I'll take that extra electron so I can fill up my electron configuration. So we're gonna skip skip out on tungsten because it's not an exception, but these others are. So for chromium, we look at chromium in a periodic table. It's the argon core. And then we come into the periodic table on row 4, so we know it's a 4s. And we're going to hold off on that until we get to the 3ds. Okay. It would be 4s2, 3d4, but 3d4 is really close to 3d5. And 5 is a magic number. I mean, it's a half-filled D shell. So I'm going to put a 5 there and a 1 here. 4s1, 3d5. Molybdenum's right below that, so it's the krypton core. We come in on the 5th row, so that's 5s, and then it's a 4d. And so that's going to be 4d5 and 5s1. So see, they have a very similar electron configuration, and they want that half-filled D shell, enough to steal that electron. Now copper, silver, gold. Let's look at copper, argon core. Comes into the periodic table now at row 5, so it's 4s. And then 3d. And it would be 3d9. That's close enough to 10 that it's going to steal that electron, because it's going to be 4s1, 3d10. Silver is a krypton core. Comes in on the 5th row, so 5s, 1, 4d10. Now that we're getting comfortable, don't mess up on gold. So gold, we get down there and it's got the xenon core. Then 6s, 1. But don't forget now we have those 4f, so it'd be 4f, 14, and then we have the d's, and so that would be the 5d, 10. So if you get comfortable with the first two and then you forget the f orbitals. Okay, so don't do that. Gold has got that f block completely filled and the d block completely filled and just the s1 so that it could fill that block. Okay, when you get to mercury, then we put that electron back in the s and we have a 6s2. Okay, so now we can answer the Alex questions about all of these. So this is saying is some unknown gas. G stands for the noble gas core. N, M, or O stand for integer numbers like 0, 1, and 2. And so here's the electron configuration. And so, what blocks do we see? Well, we see an S block, right? And we see an F block. Okay. And so where do you think this is? So we have some electrons in the S, some electrons in the F. It's saying what blocks do you see? So we see an S block and an F block. And so where do you think this metal, or I just gave it away, where do you think this element is in the periodic table? It's down in the F's, right? It's a MF7, so it's the 7th one. It's like gadolinium, and that's a metal, so it's a metal. Okay, well, here we go. This is another one. We have an S and a P, so we can mark an S block, a P block, and we're P6. Okay, it's way over there. It's a noble gas, so that's going to be a non-metal. Now, it might be one like silicon or germanium or arsenic or antimony or tellurium. Those would be the metalloids. So what would be this? Well, we guess we don't know if it's the 4F7 or the 5F7, so we really can't tell. But we can tell what block it is in. 1, 2, 3, 4, 5, 6, 7. So gadolinium or californium. So this is either G, D, or C. Or is that curium? That's curium. Californium is CF. So curium, named after Marie Curie. And then we know this NS2, NP6, that's going to be a noble gas. So It's going to be like neon through radon. Okay, let's try another one of these. Here we have an S2 and a P5, so we got an S block and a P block. And then it's a P5, so it's way over there on the right. It's going to be a halogen, so that's a nonmetal. Here we have an S and an F, okay. 10th one in the F. Still, all the F blocks, those are all metals, so it's going to be a metal. So this might be like fluorine through AT. It's a halogen. And this one, the 10th one on the F block. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So HO or ES. Again, those are metals. All right, we made it. 9:48. So electron configurations. It's not too bad. It tells us all about the chemistry of the element.